Hello students, this is the second video presentation of Lesson 1. We're going to cover Chapters 3 and 4. Chapter 3 is the resultants of coplanar force systems, and this will be covering item number 6 on your objective sheet. Find the resultants of concurrent and non-concurrent coplanar force systems using the parallelogram theorem and method of components. Okay, in this slide we're seeing a force system which happens to be two tugs pulling on a barge. Okay, the resultant of this force system is shown here in this force triangle as R. Okay, so what we're looking at here is an oblique triangle, in which case we're going to use the parallelogram method, and this is drawn here with the force parallelogram. So how are we going to find the resultant? Okay, we're going to use the law of cosines, where the resultant squared equals P1 squared plus P2 squared minus 2 times P1 times P2 times the cosine of phi. Okay, and then we're going to find the direction using the law of sines. We're going to compute the x and y component, or we can do this by the method of components. I'm going to kind of leave this up to you, whichever you're more comfortable with, but we can also do it by the method of components, which is a little bit easier, a little bit more brute force. So we can compute the x and y component of each of the forces. So each of the tugboat has an x and y component. We can add the x and y force components together individually, and then we can calculate the resultant and the direction using the equations of a right triangle. That would be the second way to do that. So graphically depicted, the resultant by method of components looks like this. Okay, we have force 1 and we have force 2, and then here would be our resultant. We draw the parallelogram. So what we're showing here is this is the component of force 2 in the x direction. This is the component of force 1 in the x direction. We add those two together. And then over here we have the component of force 1 in the y direction. We add that to force 2 in the y direction, and then we get the resultant of the y. So once we have the resultants of the x and the resultant of the y, we can use just our regular equations to figure out what the resultant is. Those would be the regular right angle. So essentially that would be the hypotenuse of these two sides, Rx and Ry. Now, the beauty about the component force system is we can do this with not just two forces. We could do this with 4 forces, 5 forces, 6 concurrent forces. We can add them all together, doing it the same way. And really it's the same process. What we would do is take the x and y components of each and every one of these forces, and then we'd add them together. And if you're going to do that, a table like this would help to keep it straight in your head. Okay, so in this case we had these 4 different forces, and we found the x component, and then we found the y component of each one of those 4 forces, and then we summed them up together, and then we get the x and the y component of the resultant. So if that's a little bit easier for you, that's good. Moment of the force. We're going to talk a little bit about moments of a force, but really this comes up when we start talking about the beams. So I'm going to kind of minimize our discussion about that here and now. These are just examples of how to create a moment. So you have a force acting at a right angle of a moment arm to a point, okay, and then that creates a rotation about that point, and that's a moment. Okay, so Chapter 4. In Chapter 4 we're going to introduce the term, well, you already know the term equilibrium, but we're going to talk about what we can do with equilibrium. Okay, so statics deals with the action of forces on rigid bodies at rest, or of zero motion. Okay, so when you talk about a rigid body at rest or zero motion, you're talking about equilibrium. So by definition, when a system of forces is in equilibrium, the resultant of all the forces acting on each body in the system is 0. Now, For a body to be in equilibrium, the resultant of all forces, like I said before, acting on the body is zero. The three laws of equilibrium of a body being acted upon by a coplanar force system are: the sum of the forces in the x direction are zero, the sum of the forces in the y direction are zero, and the moments about any point also equals zero. Now, why did I use this term coplanar up here? Coplanar force system. If this was a three-dimensional force system, I would also have the sum of F of Z in the third dimension. Okay, so when we're talking about coplanar here, we're just talking about the X and Y plane. Okay, let's talk about the free body diagram. So in most problems in statics are due to interaction of bodies. To solve these problems requires that isolating the body to examine the forces acting on it. So what we do is we draw a free body diagram, which is essentially just a sketch. And what that sketch is, it shows the body isolated from the other bodies in the system, and it shows the external forces acting on the body due to its interaction with the other bodies in the system. Now, what does that mean? Okay, so let's take a very simple system here. This is a weight hung by the rope. Essentially, we have two bodies in this system. We have the weight, and we also have the rope. Okay, so now we're going to draw a free body diagram of the rope, which is just a straight line for the rope. We have a reaction force at the top, and we have this force here pulling down due to the gravitational force of the weight. Okay, and then if we were to draw a free body diagram of the weight itself, we have the gravitational force by virtue of the body's weight, and then we have the reaction force here at the screw eye, which is essentially the tension in the rope that's holding the weight up. So then, in a very simple case, that is a free body diagram of this system. Here's another example of a free body diagram. Here we have a weight that's supported by two ropes tied together with a knot. Okay, now for solving this problem, the ideal place to draw your free body diagram is at the knot. Okay, so what we have at the knot here is we have a tension in one rope that comes off here at this angle. We have the tension in the other rope that comes off at the other angle, and those tensions are based upon the weight here, the gravitational force due to the weight that's being supported. So that is the free body diagram of the knot. Here is another system. For example, what we have here is a cylinder that's supported by a beam and a flexible cable. Okay, if I was to look at all the forces acting on this system, I have this sketch here A. We have the tension in the cable, we have the weight of the beam, we have the reaction forces at point A, at the pin. And then we also have the cylinder here, which has a weight of itself, again, acting in vertical direction. And then we also have a reaction of the cylinder pressing on the wall. Okay, so in this case, we have two bodies. We have the cylinder and we also have the beam. And what we're showing you here is the free body diagram of both the cylinder and the beam. Okay, in this case, here's the cylinder, here's the reaction to the wall, here's the weight of the cylinder, and here's the reaction of the beam onto the cylinder. Now for the beam, we have the X and Y reactions at point A, we have the weight of the beam, we have the force due to the contact with the cylinder, and we also have the tension in the cable. Okay, so the beam is essentially a non-concurrent force system. Now, one more thing I want to talk about is a two-force member. Okay, a two-force member is really, and this is a picture of one, it really has only a one force and then its reactive force. So really a two-force member is a special case. Now if we can look at a statics problem and identify a member as a two-force member, it helps us to solve the problem. Okay, so a two-force member is a special case where the member is acted on by two equal and opposite forces, and the member is assumed to be weightless. Or the weight of the member is rather insignificant when compared to the forces acting on it. So the examples of what a two-force member are would be, I'm going to look at the next slide here, the cable RQ in this next slide. Okay, so we have this flexible cable here. Okay, we know a cable, a rope, etc. can only handle tension. Okay, so in which case we have the tension in the cable. So that is a two-force member. And then this here is a boom. Okay, it can only handle tension and compression. We're going to assume that the forces due to this weight here are more significant than the weight of the actual boom itself. Now once we make that assumption and call the boom a two-force member, it helps to simplify how we solve the problem. Here's with our force triangle, and then here is our free body diagram. If we didn't call this a two-force member, we would have the weight of the beam to deal with, and we would have different reaction forces here, so it becomes more of a non-concurrent force system. But in this particular case, we got a two-force member. It allows us to draw a free body diagram at point Q and easily solve this problem. Okay, so there's problems in this section on problems. We're going to talk about problems in the other presentation. Thank you.